Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
For nearly half a century, physics harbored a ghost. It was a perfect state of matter, a macroscopic manifestation of quantum mechanics that defied all classical intuition and resisted every theoretical assault. In 1911, Hayek Camelingons, working in his Leyden laboratory, cooled mercury to a temperature of 4.2 Kelvin and observed its electrical resistance vanish completely. This discovery of superconductivity presented a paradox of the highest order. The established understanding of metals, even with early quantum refinements, envisioned a chaotic sea of electrons scattering off lattice imperfections and thermal vibrations. How could these same electrons, particles defined by their mutual Coulomb repulsion, conspire to form a collective, dissipationless current? The phenomenon was experimentally undeniable, yet its microscopic origin remained one of the most profound and persistent mysteries in science. By the late 1940s, the problem had acquired a legendary status, a theoretical behemoth that had humbled a generation of the world's most brilliant physicists. The initial attempts to tame this enigma were phenomenological triumphs, offering elegant descriptions that circumvented the need for a microscopic explanation. In 1935, brothers Fritz and Heinz London developed a set of equations that masterfully characterized the electromagnetic behavior of a superconductor. Their framework postulated a relationship where the supercurrent density is proportional to the magnetic vector potential. This formulation led directly to a stunning prediction, soon confirmed experimentally as the Meissner effect, the complete expulsion of a magnetic field from the superconductor's interior. The London theory introduced a characteristic length scale, the London penetration depth, lambda sub L, describing how far a magnetic field could penetrate the material's surface. While immensely powerful for predicting outcomes, the London equations were akin to Kepler's laws of planetary motion. They provided a precise mathematical description of the phenomenon, while offering absolutely no insight into the underlying force or mechanism responsible for the behavior. The theory began with the superconducting state as a given, a black box whose inner workings were a complete mystery. 15 years later, in 1950, London Ginzburg and Landau constructed a more sophisticated theory. Building upon Landau's work on second-order phase transitions, their approach introduced a complex pseudo-wave function, the order parameter psi, whose magnitude squared represented the local density of superconducting electrons. This powerful concept allowed for a thermodynamic description of the superconducting state and its spatial variations. The Ginzburg-Landau theory successfully described phenomena at interfaces between normal and superconducting regions and introduced a second fundamental length scale, the coherence length, or 11, representing the distance over which the superconducting electron density could vary without a large energy cost. Their formalism was a significant intellectual advance, bridging thermodynamics with quantum concepts. Yet, it too was fundamentally a top-down theory. It provided an exquisite language to discuss the superconducting phase, but the identity of the order parameter psi and the microscopic interactions that produced it remained profoundly unknown. It was a detailed map of the ghost's behavior. The ghost itself remained the decisive clue, the Rosetta Stone that would finally translate the phenomenon into the language of microscopic physics. Arrived in 1950 from two independent laboratories, Emanuel Maxwell at the United States National Bureau of Standards, and a group led by C.A. Reynolds at Rutgers University. Both investigated the superconducting transition temperature, T sub C, for different isotopes of the same element, specifically mercury. Their findings were unambiguous and startling. The critical temperature was found to be proportional to the isotopic mass raised to the power of approximately -1/2. This relationship, T sub C is proportional to m to the power of negative alpha, where alpha is near 0.5, was a revelation. It provided the first concrete evidence that the crystal lattice was an active participant in the phenomenon. The mass of the atomic nuclei, which determines the frequency of lattice vibrations, was directly influencing the onset of superconductivity. Purely electronic theories were rendered obsolete. The interaction had to involve the lattice vibrations, the quanta of which are known as phonons. The problem was one of electron-phonon coupling. This discovery immediately galvanized the theoretical community. Herbert Frerley, seizing upon the isotope effect, proposed a theory that same year, which for the first time identified the correct mediating particle. He theorized that an electron moving through the crystal lattice could polarize the surrounding positive ions, creating a transient region of excess positive charge. This distortion, a cloud of phonons, could then attract a second electron a short time later. This was the essential insight. A phonon-mediated attraction could, in principle, overcome the electron's direct Coulomb repulsion. Frehley's work was a conceptual breakthrough of immense importance. It pointed the way forward. However, his mathematical formulation, while correctly predicting an isotope effect, failed to produce a stable, lower-energy ground state for the system as a whole. He had identified the crucial interaction but was unable to construct the correct many-body quantum state from it. The stage was thus set, the clues were assembled, the culprit particle was identified, and the limitations of prior theories were clear. The challenge now was to build a quantum mechanical wave function for a sea of electrons that, through the subtle dance of lattice vibrations, could find a collective state of perfect, dissipationless harmony. It was this specific, well-defined challenge that John Bardeen, Leon Cooper, and Robert Schrieffer would ultimately resolve. The intellectual puzzle of superconductivity found its first crucial piece in 1956. Through the work of Leon Cooper, working at the University of Illinois under Bardeen, Cooper addressed a simplified, yet profound, question. He considered two electrons existing above a quiescent sea of electrons, the Fermi sea, interacting via an attractive potential. His calculations delivered a startling result. An arbitrarily weak attraction, of the kind mediated by phonons, would bind the two electrons into a paired state. This bound entity, the Cooper pair, possesses a lower energy than the two individual electrons. This outcome was deeply counterintuitive. It revealed that the stable ground state of the metal was unstable against the formation of even a single such pair. The implication was immense. The true ground state of a superconductor must be a collective state composed entirely of these pairs. Cooper demonstrated the fundamental instability that drives the transition, providing the conceptual key. The challenge remained to describe the quantum mechanics of the entire system, a sea of overlapping Cooper pairs. This task fell to John Robert Schrieffer, a graduate student who, in a moment of celebrated insight on the New York City subway, conceived of the necessary many-body wave function. The mathematical form he devised is a testament to quantum elegance. The Bardeen-Cooper-Schrieffer ground state is represented by the expression psi subscript BCS equals the product over all electron momentum states k of the quantity U sub k plus V sub k times the creation operator for an electron with momentum k and spin up times the creation operator for an electron with momentum negative k and spin down, all acting upon the vacuum state. Here, the terms U sub k and V sub k are complex coefficients representing the probability amplitude that a pair state k is empty or occupied, respectively. This brilliant construction describes a coherent superposition, a condensed, where all electrons are paired. It is a single quantum state of macroscopic scale, where the motion of every electron is correlated with another, forming a rigid system resistant to small perturbations. John Bardeen, the intellectual leader of the trio, orchestrated the synthesis of these ideas into a complete, predictive theory. The framework built upon Cooper's pairs and Schrieffer's wave function yielded a cascade of verifiable consequences. The theory's central prediction was the existence of an energy gap, commonly denoted by the Greek letter delta, separating the paired ground state from the lowest energy single-particle excitations. This gap is the energy required to break a Cooper pair. Its existence provided a direct explanation for superconductivity's signature properties. Zero electrical resistance emerges because scattering events, which normally dissipate energy, lack sufficient energy to break the pairs and create excitations. The electrons flow as a collective fluid, impervious to the usual obstacles. The Meissner effect, the expulsion of magnetic fields, arises from the phase coherence of the wave function, which allows the superconductor to generate persistent surface currents that perfectly cancel any external field. The theory, published in 1957, was met with immediate, spectacular confirmation. The definitive experimental evidence came from the work of Giaever at General Electric. Giaever devised an elegant experiment measuring electron tunneling between a normal metal and a superconductor, separated by a thin insulating layer. The current voltage characteristics he measured revealed a direct signature of the energy gap. At low voltages, virtually no current flowed, as electrons from the normal metal lacked the energy to overcome the gap and enter the superconductor. As the voltage increased to a value corresponding to the gap energy, the current rose sharply. Giaever's measurements of the density of states for the excitations revealed a shape that matched the BCS predictions with stunning precision, providing irrefutable proof of the theory's core tenets. The legacy of BCS theory extends far beyond the phenomenon it was created to explain. The mathematical formalism, particularly its concepts of spontaneous symmetry breaking and a collective gapped ground state, became a foundational paradigm in theoretical physics. Philip Anderson recognized that a similar mechanism could give mass to gauge bosons in relativistic quantum field theory, an insight that directly contributed to the development of what is now known as the Higgs mechanism in the Standard Model of particle physics. Furthermore, Brian Josephson, a graduate student at Cambridge, used the BCS description of the superconductor as a macroscopic quantum object to predict that Cooper pairs could tunnel through an insulating barrier between two superconductors. This phenomenon, the Josephson effect, was soon observed and has become the basis for SWID, or superconducting quantum interference devices, instruments of unparalleled sensitivity for measuring magnetic fields. In conclusion, the theory of Bardeen, Cooper, and Schrieffer resolved a half-century-old mystery, transforming condensed matter physics from a largely empirical endeavour into a field with a powerful predictive, microscopic foundation. It provided a conceptual toolkit for understanding emergent collective phenomena, with its influence permeating areas from the superfluidity of helium-3 to the structure of neutron stars, while modern research into high-temperature superconductors has revealed materials where the phonon mechanism is insufficient and new pairing clues are sought. The foundational concept of electron pairing and the formation of a coherent, gapped condensate remains the central organizing principle. The work of 1957 stands as a monumental achievement, a pillar of 20th century physics, whose intellectual reach continues to shape our understanding of the quantum world.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.